Hello, everyone. So I'm really happy to be here with you to present today at Percona Live. And yeah, today we'll be talking about open source databases, analytics, and how to really create performant and concurrent analytical APIs. So a little bit about myself. My name is Igor, and I would say that I'm a real fan of data visualization and data analytics. Like, the best way for me to spend my spare weekend would be just to code something which tells a story with data, with metrics, and sometimes those stories are really grueling, or they might remind us of different things in our lives, and not all of them are great, but anyway, it's fun to be able to crunch the data and to tell the story with it. So today we'll be talking about analytical apps, and this talk is for you, the application developers. They work with analytics, and as a short visual hint for you, just I've created this slide. So if your applications are anywhere like this one, if you work with charts, with metrics, with different facts that you present in this way, this talk is for you. So let's talk about what makes a great analytical app. So obviously, in most cases, these apps are user-facing, meaning that people do interact with them and they expect that these apps will respond to the actions within a reasonable time. So I won't be reiterating and repeating numerous scientific papers on that subject, but UX experts, they tend to think that if an application doesn't respond in less than 1 second, or then it's not that useful, it's not that fun to work with. So a great responsive app that presents analytics should be able to do that in less than 1 second. And I would also claim, and that's not the only bold claim that I'll do during the course of my talk, that a great analytical app should also be reliable, meaning that it should be able to serve as much load as it gets. And just as a small reminder for you, I just wanted to say that, well, we don't have so much time in a day, so 60 seconds times 60 minutes and 24 times 24 hours, it is only slightly more than 80,000 seconds. So if we have like a dozen customers, and every single one of them would make just a few requests to our app, that will bring us to the level of 1 request per second, and even more if we do have some if the load is not evenly distributed over time, and but obviously it is the case because people tend to have some sleep in the night, and the situation gets even worse if we have any seasonal patterns in the usage which are not only on daily level but on weekly and monthly level. Well, the Black Friday comes, and then we need to make sure that the application we are building can withstand the load of dozens RPMs. So how do we make sure that this is possible? For that, for these kinds of analytical APIs, analytical apps, we need to have great analytical APIs in place. So that responsiveness and reliability translates to the requirements for latency and concurrency. Of course, we've got a lot of tools and ways to make to optimize our apps. So we can pre-render the content and use server-side rendering, or just make our apps as lightweight as they can be. We can employ different kinds of databases, like non-relational key value stores, to serve session data and user profiles. However, it still leaves us with the requirement to have great analytical APIs, which will serve the requests with under 1 second latencies, or maybe even less, because we need to account for the round trip between our servers and CDNs and users spread out all over the world. And we also need to make sure that even if the traffic spikes, our apps will be able to accommodate that. So low latency and high concurrency for analytics, is it even possible? I believe that maybe in the next 45 minutes, we'll get a really great and clear answer to this question. So to bring us to a common ground, let's start with some basics of analytics. A short 2-minute introduction to that, so we speak the same language during the next 45 minutes. Okay, I believe that every one of you have heard this 4-letter word, OLAP. So online analytical processing is as simple as being able to answer multidimensional analytical queries with short latencies or swiftly. But what are those multidimensional queries? Basically, queries formulated under MDA are queries which are structured with dimensions and measures. So it may sound complicated, but it's not, but it's really not. So dimensions are really like labels or just words that you use to name different categorical data items in a data set. Like those are basic business logic items, or all the words from your domain that you use to reason about your data. People, customers, orders, or like page loads, page hits that you use while reasoning about your data. And measures are the numerical values that you calculate for those dimensions. Measures represent the quantitative part of your data. And the tricky part is that usually your raw data that you store in a database should be processed to calculate their values for measures. And the process of calculating the measures is called aggregation. So you need to use aggregation functions for that. And the other tricky part is that often you need to process the whole data set or large chunk of your data set to calculate the value for a measure. So the choice of aggregate functions might lead or might present the risk for performance bottleneck, but we'll cover that later in the talk. So just for the sake of giving you an example, let's imagine that we have a data set which is structured like that. So we have a large fact table named line item, which basically contains different facts about orders made in an online store. So it has keys to different dimension tables, like order key or part key or supplier key, and we can use this data set to calculate different measures, like the count of line items would basically tell us how many facts of sales were, and the sum over like quantity will get us the total quantity of items sold. So given this data set, we can issue SQL queries just like that. So here we can see that this query really tells us about what are the dimensions and what are the measures in our data. Like we select return flags and line statuses, and we group by those columns as well. So the data will be structured by these dimensions. And we can also see that we select a bunch of aggregated data. We use sums and averages and counts for that, and those things, they basically represent our measures. So I believe that maybe not every one of you, but the major part of you, my great audience, already understood that what I was showing you in the query and the data set, it was not made up from scratch. It's a part of the famous TPC-H benchmark. TPC is basically a council or an entity which is known and famous for creating trusted and representative benchmarks that are used to test the capability of the hardware and the software, meaning databases, and to compare their performance. So this TPC-H benchmark and data set is a so-called decision support benchmark, meaning that it's made to benchmark analytics and analytical workloads. So it may be tuned in size just by choosing a scale factor. So you get a data set of a particular size which you can upload to a database, and this is kind of important because by choosing the scale factor, you can get a data set which would be like 100 gigabytes, and probably you'll be able on a certain configuration to fit it into your machine's memory. And you can also create a data set which would be like 100 terabytes, and it hardly would it fit into a memory of any server out there. So you need to use some distributed database or a data warehouse to store the data and to perform the benchmark. And what's important, that this TPC-H benchmark is supplied with 22 analytical queries, and you're already familiar with one query from that set, which can be run to get the understanding of how performant a particular database on particular hardware is. So if you go to the TPC website and flick through those different benchmark results, you'll notice that some of them are of the first kind, where all data fits into the memory, and what we actually benchmark is the ability of a database to quickly crunch the data and to have in memory, and to have efficient implementations of different algorithms. And often you'll find that the hardware used for those benchmarks, it's I would say it's not sexy in 2021. They are like servers with multiple CPUs and tons of memory, and it costs a lot of money, and hardly would you think, I believe, in your current circumstances of bringing one or more servers like this to a data center and having them as a dedicated computing servers for your workloads. So chances are that you'll be thinking more about using cloud-based data warehouses or query engines to work with data. So let's explore what kind of results does this benchmark get, and what might be the starting point for our pursuit for low latency and high concurrency. So often what you would see is that the queries differ in amount of time that it takes to run the query to get the results, but the mean or average latency would be about like you can see on the slide 33. And if you wonder 33 what, I would say 33 seconds. So it's really not that easy to on a data set of a fair enough size to run those queries and hit very low latency. So you might see like 33 seconds or and of course this result differs for different queries, but never would you spot like milliseconds or even less in there. So you may wonder, but what happens if someone takes not just a traditional database on a really upscale server, but takes a modern data warehouse or a query engine running with a fair amount of performant compute nodes and run this query. So here are two examples. The same query run on Snowflake, and the first one is run over instances over like compute warehouse of small size, and as you can see, the total time of running this query is just 2 minutes. So when you get like 33 seconds or so on a really advanced server with like small data warehouse in Snowflake, you might get 2 minutes. No user would tolerate this kind of latency. But if we switch to X large warehouse, we can get a better number. So it's slightly over 8 seconds now. However, I don't think that it's something that you would tolerate in your app if you have an API which talks to Snowflake and serves the data with 8 seconds plus latency. That's just hilarious. So I would say that the current state of regular databases running on regular hardware or even advanced hardware and modern data warehouses and query engines are running in the cloud is so the latencies that we get as application developers is really below our expectations, because it doesn't allow us to provide the user experience in our analytical apps that would be perceived as great or even desirable. So what about concurrency? Here's an interesting chart, an interesting benchmark. This benchmark is interesting because it was exploring how fast ClickHouse can, which is obviously a great analytical database and really performant. How fast ClickHouse can answer to a simple select one queries. As we can see right now, the results are really same no matter what kind of protocol we use to talk to ClickHouse, either whether it is HTTP or TCP. We can see that when their concurrency level rises more than 16 RPS or 32 RPS, then the response time grows and it does so really fast. But I want to remind you that those were only just select one queries, so no processing was done to serve those requests. Like the query planning was really simple, and no data needed to be read from disks or from of our in-memory cache to serve those requests. And if we start looking for some number on data warehouses and query engines, we'll see that BigQuery usually don't say that we should expect anything more than 100 concurrent requests, and even less so for Athena. So Athena provides 20 concurrent requests, and that's it. Even more, the things get even more interesting when we explore this benchmark done over Snowflake. So what we can see here is that we can get a really high concurrency, maybe 50 RPS or 100 RPS. However, the most time that is spent during the execution of those requests is spent in a queue. So what you get here is the exhaustion of the compute nodes. So you need to wait until the requests which came previously would be served. So you'll get the later requests to be processed. So as technically it is possible to have 100 RPS of Snowflake, you'll get the latency that you won't like in that case. So this kind of revelation is really evident from this chart, where the actual execution time is really slim. However, the rest of the latency is paid on just waiting in a queue. So it is sad to conclude, but the level of concurrency that we can get from modern databases running on any hardware and modern data warehouses and query engines is also below expectations. We can expect those tools to serve our requests in maybe with such characteristics as like 20 or 30 RPS. However, hardly we can expect to concurrency to rise over that level with the same level of latency. So where does this get us? I believe this is correct to say that right now we're in a state where we can get somewhat good concurrency, but low latency is really not achievable. But why so? To summarize, I would say that this kind of latency is due to the fact, and this we get back to the nature of analytical queries, and that we need to actually aggregate data to compute metrics. The volume of data that we need to process is often huge, and unlike in the use case of key value store or document database, when you use these relational databases with Snowflake, OLAPs, data schemas, you often need to scan a lot of data to get the result. And it's often the case that the data set doesn't fit into memory, and it should be distributed over several nodes on your network, meaning that for many queries, you'll need to do distributed joins and maybe even move data across your nodes to make those joins possible. So that's why hardly you can get a desirable level of latency. And concurrency really depends on how much of compute nodes you have readily available to serve your requests. So if you can make sure that there is a dedicated number of compute nodes available at all times, then you'll be good. But it's kind of costly if you if you really want to for those compute nodes to be online and ready to serve your request at all times. But if it's usually not the case, like for data warehouses, like Snowflake lets you move your data warehouse in an idle state, so it does not consume your money. And the same stands true for BigQuery, for example. So these instances are shared across different applications running on that data warehouses. So in that case, it becomes really inelastic. So this hard limit on concurrent requests, which many tools enforce on you, it's really due to the fact that if you wanted to be able to hit, like, to run not 20 or 100 requests per second this tool, but maybe 1,000, then it would mean that the whole compute cloud can become unresponsive to the requests coming for other tenants. That's why the hard limit, and there is really no workaround around that. If we speak of public clouds and shared resources we get from there. So here the sad part ends, and we really come to the solutions. And I would say that it may be totally expected and obviously totally researched in this analytical space, but the first and the most obvious solution to that is to just pre-compute the data, to create a materialized views, and to make sure that we don't need to perform at least some of computations while serving the requests. And as we all know, like materialized views are just persistent representations of the result sets got after executing a query. And a more sophisticated kind of a materialized view that can help solve our problem of bringing low latency and high concurrency is so-called OLAP cubes, or it's better to say hypercubes, because they often represent pre-computed results for a high number of dimensions. It may be like 3, 4, or maybe 10 of them. And what you can do with those cubes is just to slice and dice them, meaning you can say, well, I don't need to have this dimension in the data set, and then you can roll up their numerical values for that dimension, and to aggregate them really efficiently to compute metrics that you want to use. So again, if you look at this query, we can see that it can be served really quickly if we already have the data grouped by return flags and line statuses, and if the computation for sums or counts is already done, and even if we exclude from those query one of the dimensions, say return flag, we will still be able to compute the results faster than executing the original query, because what we need to do is just to sum pre-computed sums over this excluded return flag dimension. So it would be really more convenient and more performant. So the only problem is if we go down this materialization direction, is that while many databases have the support for materialized views on the database level, this is kind of optimization which we as application developers don't really want to use, or at all times. Like what we often use is just we'll create some kind of caching layer in our application. We'll be keeping track of the queries that we run against our database, and we'll try to serve the queries from that. And the other downside of this approach is that well, we're really dealing with SQL here, so we should make sure to write this SQL in a proper fashion. Don't make mistake anywhere. And well, when we need to develop new feature in our app, when we need to adjust existing ones, what we'll need to do is just to write new queries, test them, make sure that our custom built caching layer is able to cache the results of this new query, and so on and so forth. So totally possible, but not that convenient. So obviously, if we don't want to write the SQL by hand, the great way to do that would be just to generate the SQL. Really? Okay, I don't want to curse during the course of my talk, but I won't be saying use ORMs because, well, who uses ORMs in 2021? So it would really be nice for us to be able in some way to generate our SQL queries automatically based on their common language that we're already familiar with, based on dimensions and measures. So we can formulate our queries in a way, hey, I want to get this couple of measures for this couple of dimensions. This might even look like this. So we say, hey, this is my dimension, this is my measure, and I want the result set to be sorted by another dimension. Looks great, huh? So in order to do so, we should be able to represent our data set in the same terms, so in terms of dimensions and measures. So this kind of description would really help to generate the SQL and would really represent the schema of our data. So this is just another example of an imaginary data schema that we can use in our case just to define the same dimensions and measures we previously saw on that query. So yeah, we say, hey, we have this customer key dimension and we have this data dimension, and they have different data types, and they are backed by different columns in the source database. But those columns can be used to generate the SQL. So for the query that you're already familiar with, this SQL can look like this. And I believe that it looks really similar to the example query that we from the TPCH dataset that we're already familiar with. So we are selecting dimensions, we are selecting measures, which basically computed using aggregate functions, and we are grouping by those selected dimensions as well. Okay, we can also filter the results and limit them, but the queries are really similar. So while this approach is truly feasible, but it also leaves us with a number of issues. So the first one is, okay, we can create this cache using those generated queries, but how do we maintain it in up-to-date state? So we're still left with lots of boilerplate code, which should make sure that we don't serve the data which is stale, and that we update our materialized views in a timely manner. So depending on what kind of data you use in your app, depending on what the volume of that data and on the domain that you build in the application in, this kind of code to invalidate your cache and to refresh data, it may get really complex. And hey gosh, I don't believe that you like to maintain that. And there is more to it. You really need to find the right balance between how much does it cost to refresh your materialized views, and by cost I mean really money, because if you use data warehouse or query engine, which is cloud-based, you will often pay like for the amount of compute power or for the amount of data processed. And you also need to account for such things like the time-based manner of your data. So if you only append data to your data set, should you compute the materialized view over the whole data set, and just try to understand and maybe write some more code for that, which kind of data is updated and which part of your materialized view should be updated to reflect that? That's not that easy, huh? So it would really be nice. Again, let me dream here. If we would be able to say, hey, we need to have this kind of OLAP cube or materialized view, which should include this set of dimensions, say customer key or date, which is a time dimension, and this set of measures, say count. And what we want to do is just to refresh the whole materialized view to once a day. So we'll do this as a cron job to run. We'll be running this once a day. It would be nice to have it like this, right? So then we are left with just the only question. But okay, it can be great to be able to represent our data in materialized state and save it to the database. It would be great to reason about the data in terms of dimensions measures, but how do we really use that data in our app? How do we really query that data and bring that to the customer-facing layer of our app? Well, for that, we really need an API, and as we're dealing with analytics, this should be an analytical API. Again, wouldn't it be nice for us to be able just to hit some HTTP endpoint and say, hey, we need to get a result set for this set of dimensions, this set of measures, and just get it instantly with a desirable and with desirable latency? It would be nice, really. And chances are that the application that we're building, at least it's customer user-facing layer, is built with modern web technology. Well, chances are you have someone coding in JavaScript on your team. So, and that folk might be well versed with React or Angular or Vue. So, wouldn't it be nice for us to be able just to wire up some React code and just to get the result set using some kind of JavaScript load method, or just maybe a wrapper function for in React. So yeah, that would be great. But do we have the technology in place to really allow that? Well, I guess you already know the answer. So really, the tech which allows us to get an API that would speak measures and dimensions and work performantly over HTTP and maybe over WebSockets, bringing you capability not only to run ad hoc queries but also to get streaming data or support real-time update scenarios. It really exists. So here I present you and I reveal you Cube. So Cube is obviously an open source project that I'm involved with, and it is an analytical API platform which allows you as an application developer to spin up an analytical API that speaks measures the dimensions, that is performant, that brings low latency and high concurrency in minutes, and you can do that over any SQL compatible database. So what you really get is just the ability to describe what kind of data you have in any database in terms of dimensions and measures, to connect to that database and instantly be able to issue queries in terms of those dimensions and measures, and have Cube do all the rest for you, to generate the queries, to execute them against the database, making sure that those queries are orchestrated in the right way, they don't overload the database, and their results would be properly cached, and then to serve the data to your front end over an HTTP API, and enable you to consume the data using a wide number of integrations with all popular front-end frameworks. So on what this is how Cube works for you, but under the hood, it's fair to say that Cube is just a number of microservices which serve different purposes. So what you get is just a number of API nodes which would gladly accept the API requests and serve them from the cache. There would be a dedicated refresh workers, which is just another type of instance that you might have, which would not interact with your users or with requests coming from them. But instead of that, these refresh workers would interact with the data store that you have, be it any open source database like Postgres or ClickHouse, or any data warehouse like BigQuery, Snowflake, or AWS Athena. And these refresh workers would pre-calculate or materialize ahead of time the data needed to serve your requests, and that materialized views will be stored in a special and really high performant data store called, well, obviously CubeStar, which again is specialized on storing these OLAP cubes and using them to serve the requests in a really performant manner. So this is just a few microservices which you can run in Docker or as a Docker deployment, or just in your Kubernetes cloud, and that's it. That would give you this kind of API. As I said, Cube is an open source product, meaning that what you really can do is to just come and say, hey, I want this tool to speak to another database, and while there are already built-in integrations and drivers for over a dozen most popular databases, creating another one is just as simple as providing the way to generate SQL and to issue query, to send queries to the database, and often you already have some open source libraries which allow you to do that. So any database and any features that you like, because it's open source. And the last thing, but certainly not the least, with Cube, what you can do is just to issue the same like TPCH-like queries over practically any SQL compatible database or data warehouse or query engine, and what you can see on the slide is just a query issued against BigQuery, and what you get is the latency far less than a second. So here we can see that a single API instance of Cube is able to serve the requests with a medium latency of 210 milliseconds. Well, 0.2 seconds, and the latency is 40 RPS. So this is more than we can expect for the concurrency, and really less than we need to have for for the latency. So this really brings us from this state to this state, and I really think that you as applications developers really deserve that. So what I encourage you to do is just to explore Cube, connect it to the database that you work with, where you store your data set, and give it a try. So really supercharge the application that you're building and the database of choice that you're building that application on with Cube, and just get an analytical API which is performant, which is capable of having low latency and high concurrency. And if you like the result, then well, feel free to slap a star to Cube on GitHub. I'll be happy if you do that. So that's basically it. And thanks for your time. And I really appreciate you coming to my talk, and I will be happy to answer any questions that you have. So I believe we have. We don't really have any questions to chat, but if you do have any, I'll be here with you for maybe the next couple of minutes, and I'll be happy to answer them. So any questions? And while you maybe typing, I'll be happy to tell you more about Cube. You may wonder, as I was not covering that in my talk, what kind of scenarios you can use Cube in, or what kind of projects already use Cube. So the best, Dion, thanks for that question. I believe the best way to do that is just to come to Cube's website, cube.dev, and navigate to the blog and the user stories, where you can see that generally it's used by the companies that build customer-facing applications for B2B or B2C, and have embedded analytics in them. And we're really aware of different companies already using Cube, either publicly or privately, and some of them, as I said, are listed on the website, on the user stories, and the others I can just tell you about because because they come and show up on the Cube Slack, which has more than 3,000 users. They are just ranging from small Silicon Valley startups, maybe seed stage or Series A, Series B stage, to giant enterprises. And I'm personally aware that folks at like Intel, Walmart, or IBM, or even Apple are doing great things with Cube. And but don't have the. I don't want you to have the impression that it can really help you if you're kind of giant enterprise with some huge data sets and giant workloads. It's not really so. Even if you're kind of indie developer or a mid-sized company, you should really give Cube a try. So another question I have here is about adding Cube to existing monolithic database designs. What's the first step? I would say that the first step would be just to go to the Cube websites, to the Getting Started section, and copy the single Docker command and run it on your developer machine. What you'll instantly get is just a web-based wizard with a single step, which we would use to enter the credentials and to connect Cube to your database. Then you can build on that. You can You can define your data schema just by typing this JSON-like descriptions of your dimensions and measures, and then use their readily available visual tool called like Developer Playground or Query Builder just to explore your data set. It's really that simple. So just run kube in Docker, define your connect to your database, define your data schema, and basically click on measures and dimensions and see how your data is sliced and diced in a visual manner. And I really want to say thanks to Ray helping me with different links here in chat. Thank you. Ray is also part of Cube team. He's our head of community, and that's really an exemplary community that we have. A lot of features that we have right now in Cube and that they widely used. They are contributed by our amazing community, and a lot of recipes and real-world examples of how you can model your data, how you can define your data schema, or use some best practices to build your Cube deployment. They are really contributed en masse and available on our community forum at forum.cube.dev. So really give that a try if you have a spare minute. So any more questions? As you can probably see, I'm really eager to answer them, but no more questions. Okay, so once again, thank you for attending this talk. That was really my pleasure to be presenting to you today, and it would really be even greater pleasure if you just go to cube.dev and get started today. Just connect your database and see how it works for you, and just get this low latency and high concurrency API for your analytical app. Thank you.